Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. All right, module number 3, linear regression models, econometric approach. So it is important to know that this approach is different from machine learning perspective. In the econometric perspective, we're going to focus on interpretability. Interpretability is more important. In machine learning approach, the prediction is more important. Predictability is more important. So we're going to do this module in two parts. In part one, we cover the theory of linear regression models from the econometric approach, emphasizing on the validity of a bunch of assumptions. We're going to call them classical linear model assumptions. And we say that if those assumptions holds, then we can tell a story. We can say that, okay, it seems that there's this causal relationship between random variables. We are less interested in the predictability power of these models. Okay, so we have to basically set up some assumptions and we see if those assumptions hold, and if that holds, we say, okay, statistically we have a story to tell. In the second part of this module, we will examine the process of performing linear regression models using Stats Model API. So this Stats Model is a Python package, it's very popular, and it is mostly used for econometric approach of doing linear regression. So without further ado, let's jump into it. So module 3, linear regression econometric approach. So again, my assumption is that you have seen regression analysis before, and now we're talking about the details of econometric approach very briefly at a very high level. We're going to review those assumptions very quickly in all-in-one sessions, and hopefully we get a sense that why those assumptions are important and what will happen if any of those assumptions are violated, and why we should not trust on the result of the linear regression outcome when those assumptions are violated. All right, let's start with the definition. What is econometrics, right? So what is it exactly? Well, think of it as a detective toolkit in economics, right? Where we use a bunch of statistical methods to dig deep and find out the whats and whys of economic relationships, right? And don't be fooled by the term economics. We can use econometric to estimate relationship between any kind of random variables. So typically, the goal of econometrics analysis is three things. We use it first thing for estimating, right? So we use it for estimating the relationship between random variables. It's like understanding how one thing affects another thing, right? And we also use it for testing hypotheses. Now, for example, we have a theory and we want to know that if that holds water or not, right? And remember, many times there's no theory for that, and we're just curious. And that's where econometrics is going to come in handy in helping us if the relationship is just spurious correlation or it is statistically significant. Basically, we're kind of testing if that relationship is purely correlation or it's a causation thing. So imagine, we can think of what is the relationship between Fed chairman height and interest rate, right? So this seems very stupid. It's ridiculous, right? But why should be a relationship between a Fed chair height and an interest rate? But if you run the data, at least in US for the past 20 years, you see that the correlation is high. But we know that this must be a spurious correlation. So econometric is going to give us a tool to basically tell us that, hey, this relationship that you're finding, it's spurious correlation because this and this and this assumption is violated. So it means that that's correlation. That's nothing like causation. And then lastly, we're going to use econometric for prediction, right? So predicting basically the target variables. And this is where econometric and machine learning overlap, right? So I hear from many students, they say that you think that econometric is purely used for interpretability. No, we can use it for prediction as well. But the thing is that now with the more complex and advanced machine learning and deep learning models, when the data is super complex, simply machine learning, deep learning models are going to outperform econometric. So we're not going to use econometric for the sake of its prediction power. We're going to use it for the sake of giving you the power of being storyteller. So that's why we use econometrics. Okay, now let me walk you through to the steps of the econometrics analysis, right? So this is a really important slide, so pay attention. So the steps are specifying the regression model, collecting data, and finally quantifying that model. But let's see, what are we doing here? So imagine, and guys, pay very good attention to the terminology that I'm using. So imagine you're interested in the relationship between a bunch of random variables in the population. So I'm going to write the term population. So you want to see what is the story between wage and, let's say, age and education in the entire US population, right? So this is, imagine this is your population, is entire US labor workforce. Then, so you have to specify a model. So you're going to say that, okay, I'm going to assume the relationship between wage and education and age is something like this, right? So we're going to say this is wage, and it's going to be, let's, for the sake of argument, we're going to assume that they're linearly related to each other. It says that, okay, there's going to be some constants, right? So we're going to talk about these details later on, but it's linearly related to the age. I'm going to call it beta 1 age plus beta 2 education. So if I assume that, for example, education changes, something will happen to the wage, right? What else? So you might say, let's try, for example, talent, right? Talent is important. Talents, we are going to think of, for example, gender. So I'm going to use the dummy variable, female or male. So it's a better thing. So male, if male is equal to 1, it means that we're talking about males. If it is equal to 0, we're talking about female, right? Something like that. And then, so you say, okay, you are interested to see what is the relationship in the entire population between these random variables. And there are lots of other things that you can think of, but at the end of the day, you're going to say there are lots of other things that you don't know, you don't have the luxury to have data, or basically you're simply ignoring. You're going to put it in something called the error term. Okay, so this is your error term. This is the single most important thing that you should understand when it comes to econometric approach, right? Everything is about all that error term. So the assumptions are all built around that error term. Okay, so this is your regression model. This is step 1. You're interested in doing that. Then in step 2, you're going to say, okay, now let's go ahead and collect data. Sometimes you do it, together, right? So you're thinking of the data and then you say, okay, this is the data. Now let's think about the model. But it really doesn't matter which one comes first. So these are the steps, right? So step 2, you say, okay, I need information for wage and I'm going to go ahead and collect it. But right away you realize that you cannot collect the information for the entire population, right? So that's where the term sample is coming from. So we're going to say, you know what, out of this population, let's pick a sample. Let's say a sample of size 1000, and hopefully it's randomly selected. If it is not, it's going to make some the biases. We're going to talk about those things. Actually, that's the first assumption in econometric, right? So let's say we're going to collect thousands of individual information for wage, the same story for age and education and etc., right? And then you get to this variable talent. You know that talent has something to do with people's wage. At least this is what you're hypothesizing, right? Remember that second aspect, the second goal in econometric, testing hypothesis. You want to see what is the relationship between talent and wage. But the problem is that you cannot collect information on talent, right? So how do you quantify that? So in order to quantify that, so sometimes you can come up with something called proxy variable, sometimes you cannot. So here, for example, for talent, what we can use as a proxy variable, it's something like IQ, right? So maybe IQ is a good proxy variable. And then we're going to replace talent with IQ and then to put it in a model. And then there are some other variables that not necessarily we can always those variables in the data, right? So I don't know, for example, you're very curious about the data ethnicity for individual's ethnicity, but for whatever reason, you don't have access to that one. So you have to remove it from your regression model, right? Or for example, for whatever reason, you don't have access to the gender data, so you have to remove it from the model. As you can see, there are two things going on here. So there are some variables that you don't have data for them. And there are some variables that you're simply ignoring them. So whatever they are, we're going to put them in the error term. And of course, this error term is part of the error as well. So it's part of noisy data as well. So that U term consists of noise, some variables that you're ignoring, and some variables that we don't have the luxury to have data for that. So we're going to bump them up all in the term called the error term. Okay, so that's step number 2. And then finally, step number 3, we are going to, let me actually write this number 2. We are collecting data in the sample, not the population. And then finally, step number 3, we are quantifying the model, right? So how do we quantify the model? We need an engine. So let's say This is my engine. We can literally call it engine, whatever it is, right? And then the input of this engine, is basically some data. So the data that you collected. So the data is here, and you have your regression model. So the model is there. This is part of your engine actually. And then we're gonna do some magic. So I'm gonna call them estimators. We're gonna use a bunch of estimators to give us the values for the parameters, right? So those estimators can be anything. Can be, for example, ordinary least square. Think of them as engines, right? It can be maximum likelihood estimation. It can be, I don't know, generalized least square, you name it. Generalized method of moments, FGLS, and etc. etc. So those are different engines that we can use, and the job of that engine is that take the data and we have the model and then give us some outputs. What are the outputs? The outputs are the estimated version of this model, right? Guys, remember, this model is what ideally what you can have in the population, but we don't have access to the data in the entire population. We use a sample. Because we're using a sample, those numbers are estimated numbers. So we're going to rewrite this regression model after estimation, something like this. It's going to be your wage hat. I put a hat on top of it because it means that this is simply, these are the prediction of the wage, right? And it's an estimated version of your beta 0, which is beta hat 0, estimated version of your beta 1, which is beta hat 1, and etc. Right? So let me do beta hat 2 education. And that's it. This is going to give us an exact relationship between predictions of the wage and some random variables on the right hand side and some numbers, right? So the job of this engine is to give me this beta hat 0, beta hat 1, beta hat 2, and etc. In general, beta hat j, right? If I have these numbers, that I can plug it into a formula to come up with some predictions, right? So let me give you an example. So for example, I say the prediction for wage is, let's say beta hat, I don't know, for the sake of argument is, imagine these are hourly wages, let's say 1 plus, and then for age, I don't know, for age, well, let's stick to the education for the sake of argument. Let's just focus on the education part. Let's say it's 0.5 education. And yeah, that's it. Then what does it mean? It means that if education is 10, then you're going to multiply it by this 0.5. So you get 5 plus 1. So you get 6. So for a person that's its education is 10, the hourly wage is going to be $6 per hour, something like that, right? So as you can see, this quantifying the model is going to enable you to come up with a story, right? But now the really important thing is that why was I able to tell that story, or basically what gave me the power to interpret the model like this? If education increased by 1 unit, then on average wage is going to increase by, let's say, 50 cents, right? So in order to answer that question, we have to check a bunch of assumptions. We're going to say that if these assumptions are valid, then you can tell that story. So we're going to list a bunch of assumptions. Let me actually write them. Later on, we're going to call them classical linear model assumptions 1 through 6, and say if these assumptions are valid, then your story is okay. Your story is valid. Because remember, you're inferring something from this sample to the population, right? You never have access to the entire population data. You're using a sample, and you hope that the story that you're telling based on the sample, what is my story here? Education increase, the wage is going to increase by 50 cents for every year of education, right? So if that story is valid in the sample, and hopefully I can extrapolate it to the population if all those assumptions are valid. So if any of those assumptions are violated, the numbers that I'm getting here might be off, and we're going to call it bias, right? So the story that you're telling in the sample does not extrapolate well in the population. So now our next important job is to figure out what are those assumptions, right? So before doing that, let me formally rewrite this regression model in the next slide, and then we'll take it from there. All right, now let's look at the multiple regression model, or for short, MRM, right? So as you can see, this is y is equal to beta 0 plus beta 1 plus beta 1 x1 plus beta 2 x2, beta 3 x3, and etc. And all the way to the error term, which is u. Again, this is part of it is the noise, and part of it is whatever we were not able to include in the model for because the data was not there, or we were simply ignorant, right? So this is our multiple regression model. What I want you to pay very good attention is that this is what we call population regression function. So this is what you want to basically investigate in the population, right? So it means that out there in the population, there's going to be a true relationship between your x1 and your y. That true relationship is unique, and we're going to quantify it as beta 1, right? So for example, again, imagine x1 is your education and y is your wage. When there's no hat on top of these parameters or y variable, it means that you're not estimating anything, right? And guys, remember, you're not going to ever put a hat on top of x's. X's are the observed random variables in the data in real world, right? So we're not estimating them. We're estimating the relationship between x and y. So that's why we end up putting in hats on top of betas, right? So what I want you to know, pay attention about the population regression function is that these betas, beta j's, I'm going to write it like this. Beta j's are unique. And they are unobservable. Unobservable. I want you to pause for a second and think about this. So why they're unobservable, why they're unique? So they're unobservable because they're trying to quantify the relationship in the entire population, and we know that we do not have access to that entire population. I wish I knew what is beta 1 for the entire US labor force. If education increased by 1 year, what will happen to the wage, hourly wage for the entire US population? But I cannot see that number because simply I don't have the data. So that's the unobservable part. Why is it unique? It is unique because if I have the entire population, I can use my OLS estimator and come up with just one number. Well, simply actually here, we don't need to estimate anything. If you have all the y's, all the x's, you can run a simple correlation and see what's the relationship between them, right? So it's unique and it's unobservable. And then because we don't have access to the entire population, we're going to come, the goal is to get as close as possible to this unobservable line by looking at the information in the sample, right? So there's something called sample regression function. So for example, I don't know, imagine this is all these blue dots are your population. And I wish I could collect information of all those things, but I cannot. I'm going to use a sample of them. So let's say random sample, the red one, and I call it sample regression function. And we can write the sample regression function like this. The y is equal to, and then I'm going to say, you know what? These are the estimated values. So beta hat 0 plus beta hat 1 x1 plus all the way to the term u hat. Okay. So what does it mean? So now I want you to pay attention to the beta hat j's. First of all, these beta hat j's are not unique. Not unique. Why do you think they're not unique? Because remember, we can have, out of a same population, I can have multiple different samples. So the red one is one sample, I can use green. This green one is another sample regression function. I can use, I don't know, yellow or black. So these black dots is another sample. So sample regression function 3, sample regression function 2, sample regression function 1. So as you can see, these beta hats that we're estimating, they are not unique, right? But the cool thing is that, what do you think? Are they observable or unobservable? They are observable. So this is very important. I want you to get the difference between population regression function and sample regression function, the parameters beta and the estimates beta hats, right? So these beta hats are observable because why? We use, remember, you know, this, let's say, let's focus on the black one, this sample regression function. This is, imagine this is wage and education in my sample. I see the data. I can use ordinary least square to estimate these beta hat 1. That's it. This is observable. I know that number. And our hope is that that number that we inferred from the sample is as close as possible to something in the population, which, you know, the funny part is that is unobservable. So how on earth can we test something like this, right? How can you say that, okay, this thing that you're calculating, this beta hat 1, let's say the relationship between education and wage is 0.5 or 50 cents for each unit of education, how do you know that you're close enough to population regression function, to what you're looking for in the population? The answer is practically you never know. But in theory, we're going to make a bunch of assumptions, and we're going to show that if those assumptions are valid, then mathematically, what you're getting in the sample is close to what you're going to get in the population. So we're going to call this unbiasedness later on. But remember, so that's the goal. So the goal at the very high level is tell me a story about the entire population, beta J's. I don't have data, so let's estimate some of them. So beta hat J's. So and hopefully these beta hat J's are close enough to the beta J's. Whatever I'm saying from the sample is close enough to the population. And econometric is this beautiful toolkit that's going to enable us to go from basically these numbers and get as close as possible to the true relationship in the population. And for that, we're going to make those assumptions. If any of those assumptions are violated, then the story is not there. Okay. So some terminology here. Basically, this y variable we call it dependent variable because it's basically dependent on a bunch of other random variable. On the other hand, the x's we're going to call them independent random variable. Makes sense, right? Then y is also explained variable. On the other hand, x can be explanatory random variable, right? And there are some other terms that we use. For example, y is response, x's are controls, y is predicted, and x's are predictors. And very rarely we use y is regressant and x's are regressors. And in the machine learning language, later on, we're going to see that. Let me write machine. Well, actually, let me change the pen. Let's see if I can use the marker. Oh, oopsie. All right. So anyways, in machine learning, we are going to call this y variable the target variable, and the x's are features. So this is the terminology that we're going to use in machine learning. But in econometric, mostly we do dependent and independent variable. All right. So, and as I said earlier, the goal is basically how to estimate these coefficients, right? How do we estimate beta 1 and call it beta hat 1? How do we estimate beta 2 and call it beta hat 2? It's all about that error term u. So as I said, this is going to play a crucial role in econometric analysis. Again, that u is a combination of noise, whatever variables we ignored, variable ignored, and sometimes variables that we didn't have data to collect, right? So lack of data. Okay, things like that. And then we're going to make a bunch of assumptions on that u term, and we say, okay, if those assumptions are valid, then what? All right, now let's estimate this model. Remember, this is our population regression function, and you want to estimate it by using the data in the sample. We want to come up with a sample regression function. Okay, so let's say, in the population, we have lots of data. Imagine this is all these little dots are all the information in the population. I wish I had all those dots, but I don't, right? So I don't have them. So basically what I have access to are, I ended up with this 7 observations. Let's look at that. So we are gonna do, let me use blue. So this is observation number 1, 2, 3, 4, 5, 6, and 7. So we end up having with basically 7 observations. Okay. Let me erase the extra stuff. Okay. So this is our sample, and I'm going to use these 7 numbers to come up with the estimated value for beta 0, beta 1, beta 2, and etc. We're going to call it beta hat 0, beta hat 1, beta hat 2, right? So at the end of the day, this is the data. I have something like this. Let's do y, x. I'm going to label a couple of them. So for example, this one, the blue one, this one, the x is around 18-ish. Let's say, I'm just making up some numbers. And then y is around, let's say, 8. Then let's look at the very far, and we have a bunch of other x's. So this is the 7th observation. The x is around, well, it's exactly 90. And then if I'm not making a mistake, y is 85, right? So I have this data. Remember, this is step number 2, collecting the data. And then I need to pass it to an engine. Now let's say that engine is OLS, okay, ordinary least square. And then that's going to tell us what is beta head 0 and what is beta head 1. In this case, beta head 1. In this case, our engine is telling us that beta head 0 is 0 because this is the intercept. And beta head 1, let's see, beta head 1, actually it's going to be 1 in this example because just because we're calculating the slope, right? So here's the slope. And I have, I don't know, these are 10, so 10 by 10, so 10 divided by 10 is 1, right? So, and how did we get that? What is OLS doing? So OLS, as the name suggests, it's very intuitive actually. It's called ordinary least square method, right? So what are we trying to do? We are trying to find what is the difference between what the model is estimating and what happened in reality. So for example, let's look at the purple observation. So here, in reality, the y value is, let's say 62, right? So this is 62 in reality. But what did the model predict? The model predict this number, so which is, I don't know, maybe it's 49-ish? Yeah. So the difference between these two numbers are what we call residuals, right? So the residuals are the estimated version of the errors, right? So, but just let's keep it simple. Imagine for the purple observation, so for the purple observation, the residual, we can call it u hat. So resid, is equal to y minus y hat. So y is the actual value, which is 62. Y hat is what the model predicted. In this case, was 49, right? So if you do the math, you get 13. So our residual is 13. So that was the residual for observation purple. Then for the red observation, we have another number. For green observation, we have another number. For orange, we have another number. Blue, we have another number, and etc. The brown, we have another number, and then pink, we have another number, right? So what can we do with these residuals? And if you pay attention, let me actually show you another one which is negative. So here, because the ordering in this residual matter, so u hat of the red, so this is a residual of red observation, is y minus y hat. Let's come up with some numbers. So what is y? Y is something around, I don't know, it seems to me it's close to 30, right? So this is your y. And then y hat is 41-ish. So we get minus 11. So as you can see, these residuals are going to be positive and negative, positive, negative. For the lines, for the observations above the line, they're going to be positive. For the observations below the line, they're going to be negative. So, and then there's some other terms that you should know. For example, if the residual is positive, are we overshooting or undershooting? We are undershooting, right? So for example, look at this one. Look at this one. So this is what the model is telling. The model is telling 49, but in reality it was 62, so we are undershooting. So when the residual is positive, so let me actually make you familiar with this terminology as well. So when the residual, or u hat, is positive, the model is undershooting. Guys, again, the goal of this module is to quickly review the econometric concepts. So this is a whole semester kind of thing. We're doing it in one session, so just pay attention, just be patient. And if the residual is negative, so we get the model is basically overshooting. And again, quickly, for example, here, I don't know, in reality it should be around 58-ish, but the model is predicting 78-ish, so we are overshooting. Okay, now we have a bunch of positive, negative numbers, right? So as you can see, you see some of them. So you saw 13, you saw minus 11, but just for the sake of argument, let's say we have plus 3, minus 2, I don't know, so 1, 2, 3, 4, and the brown one was large one, and we are basically there, we are undershooting, so let's say minus 20, and then plus, let's say plus 2, so 1, 2, 3, 4, 5, 6, we need one more. Let's do another positive, let's say plus 5. Okay, so these are the residuals for the 7 observations, right? What is the goal? What is a good fitted line? So if you think deeply, and when I say good fitted line, I'm referring to this line. So this is our sample regression function that we're trying to estimate, right? A good line is a line that is going to minimize these residuals, right? But if I go ahead and simply add them, so if I sum these residuals, we're going to call it u hat I, right? Over I here goes from 1 to 7. Does that make sense? If I simply add them, the positives and negatives are going to cancel out each other, right? So, and for example, and then again, remember, the goal is to minimize them, right? So ideally, we want to minimize these summation of the residuals. But the problem here is that if I simply add them, they're going to cancel out each other. So sometimes we don't get a good answer, right? So what can we do? We can go ahead and square these residuals. So pay very good attention to what I'm doing here. Because if I square these residuals, they're going to be all positive, right? So 13 is going to 13 to the power of 2 minus 11 to the power of 2, 169, 121, 9, 4, 400, 425. And then I'm going to add them up, right? So as the name suggests, so we're going to look at a bunch of squares. So this is 5 square, 2 square, minus 20 square. And visually, look at that. This is your error. If I square it, what do I get? So 2 multiply 2, I get 4. So this is literally a square. I have another square. I have another square, and etc. So we are adding a bunch of squares. And then the goal is to find the line, find this sample regression function, the red line, such that the summation of all those areas of squares is minimized, right? So that's the goal. This is what OLS is doing. Ordinary least square model. So it's going to change the slope and intercept of the line such that these squares, the summation of these squares is minimized, right? Just in order to give you a very, I don't know, the bad sample regression function estimation, imagine this is the line that we're estimating, right? Obviously for this line, the model is way off, right? So look at the error. So I'm going to go ahead and just pay attention to this. So imagine this is the error. It's crazy large. This is the error. The score is crazy large. This is the error. And as you can see, these squares are a lot larger for the black line compared to the squares for the red lines. So that's basically what OLS is doing behind the scene. This engine, this estimation technique is going to give us a tool that by changing the values for beta 0, beta hat 0, beta hat 1, what does it mean? It means that rotating the line. By changing these values, it's going to minimize the summation of the squared errors. And by doing that, it's going to find the best fitted line. So this is how OLS is estimating our population regression function and give us the sample regression function. Okay, so yeah, there are many different techniques. As I said, for example, maximum likelihood estimation, GMM, GLS, FGLS, you name it. But that's the topic for another course. Okay, now let's look into the details of interpreting the model, right? How do we interpret these numbers? Again, this is our population regression function. Just a quick review, these parameters are unique, not observable. The goal is to estimate them, but we can estimate them with different samples, so we get different numbers, so we get different beta hats for different samples, right? And now let's see how we can interpret that. So in a nutshell, we can say something like this. So imagine, but let's look at this one, for example. We say if x1 increases by 1 unit, then holding everything else constant means that holding x2, x3, k implicitly constant, and then assuming that u is constant, then the y variable is going to increase or decrease by beta 1, depending on if beta 1 is positive or negative, on average. So let me give you more context. So imagine I have wage is equal to, and imagine we estimated these things, population regression function in a sample, and we get these numbers. 1 plus 0.5, education plus, I don't know, I'm just making up numbers, 0.2 age. And yeah, and then the rest is just u hat. Okay, so imagine that's the model. Okay, and then it means that if education increased by 1 unit, then holding age constant implicitly and then explicitly u hat, well, basically we assume that u hat is constant, then on average wage is going to increase by 50 cents. Imagine the unit is dollar, so 0.5 is 50 cents, okay, per hour. So what is that? So what is the beauty of econometric multiple regression model is that it enables you to basically specifically hold everything else constant. Let me tell you what I mean by that, and then we get to the definition of partial the derivative and or partial correlation, right? So it's something like this. So in order to explain that, I need to introduce you to a concept called Venn diagrams, and I'm gonna show you how we can connect the concept of Venn diagrams with econometrics as well. So imagine this is the entire universe of the variance of wage. Okay, so this is the entire universe of wage, and then this is our education, and this is our age. Okay. Obviously, there's going to be some correlation between wage and education. Let me actually highlight a bunch of stuff here. So here, I'm gonna see, yeah. So this yellow shaded area is the correlation between wage and education. So let's set some terminology. This is a correlation, right? Then let me actually bring this back. This thing is the correlation between wage and age. Hopefully everybody is clear on these things, right? Okay. Now what we're interested is this. We want to see what is the relationship between wage and education. So I'm going to call this beta hat education or beta hat 1 in this example. So this is our beta hat 1. What is the relationship between wage and education holding everything else constant? In this example, there's only age. I'm going to hold this constant. If I hold this entire thing constant, then I'm going to say this is the net effect. This green shaded area is the net effect of education on wage, net of age, right? Holding everything else constant means that. And then this is also what we can call partial correlation, right? Partial correlation. So in multiple regression model, we're looking into the partial correlation, and this is nothing by simple derivation, simple derivative, okay? So what I mean by that, so imagine, let me actually remind you something about derivative. So the interpretation is basically narrowed down to taking derivatives, right? So imagine your y variable is equal to ax plus bx squared plus something like that. So what is the derivative, partial derivative of y with respect to x? We get a plus 2bx, right? And then we're going to say the effect of x on y is this, right? So here in our example, we're doing nothing special or fancy here. We're looking at wage is equal to 1 plus 0.5 education plus 0.2 age. If I want to see what is the effect of, look at the terminology, what is the effect of education on wage? I'm taking partial derivative of wage with respect to education, right? So what is that? 0.5. What is the effect of wage on age? It's 0.2. So then I can interpret them. I can say if age increased by 1 unit, holding everything else constant, the wage is going to increase by 20 cents per hour on average, holding everything else constant, right? And the beauty of this, if looking at these things, interpretation as partial derivative, is that now, no matter how complex your model is, you can still interpret that, right? So let me give you one quick example. I need to erase this part actually. Well, yeah, I try to keep it because probably you want to take a picture. So let's see, let me see if I can squeeze it here. So imagine for whatever reason you think the relationship between wage and age is not linear. That can be the case, right? So especially, if you're younger, your wage is lower, and then you increase, and then you get to the retirement age, maybe this is a relationship. If you want to quantify something like this using multiple regression model, what do? Hopefully you remember from your econometric courses. You're going to say wage is equal to, I have a beta 0, I have a beta 1 age, and then what? Yeah, you're going to add nonlinearity, beta 2 age to the power of 2, plus some error terms. So pay attention, this is a linear model. Because the model is linear in parameters, this is not nonlinear, but the fit is going to be nonlinear. So this is also another terminology you should be aware. So the fit is nonlinear, but the model itself is linear. So we call the model as linear when it's linear in parameters, right? But anyhow, so what we're doing, this econometric model is able to capture this nonlinearity in the data. Now, how can I interpret that? I would say if age increase, the effect of age on wage is going to change. Do you see that? So let me actually give you a contrast. So here, if I only have wage and education, and imagine this is a relationship, then for any level of education, as you can see, the relationship is constant, it's 0.5. But what if we have something like this? What if you have something like this for age? As you can see, for different values of age, if I want to think of that derivative as a slope, for different values of age, I get a different slope. So it means that the effect of age on wage depends on age itself. How can I see that in derivative? Yeah, let's take derivative of wage with respect to age. So what do we get? We get beta 1 plus 2 beta 2 age. And guys, these are numbers because at the end of the day, we're going to estimate them. Beta had 1, beta had 2, and etc. So imagine, just for the sake of argument, we get something like, I don't know, our beta had 1, let's say it's 0.2, and then beta had 2 is, it can be a negative number because this is downward sloping. Well, something like this, minus 0.1 age. Now, as you can see, if age increases, if age is equal to 0, the effect is 0.2. Let's say we are here. The slope is 0.2. If age is increasing, if age is 10, the slope is what? 0.2 minus 0.10 is 0.1. If age is 20, 0.2 minus 0.2, we get to slope is equal to 0. And if age is greater than 20, the impact of your age on wage is going to decrease, right? So if you use real data, for probably this age is something around 60-ish, closing to the retirement age, or 65-ish. And yeah, that's the case. So this is the interpretability part of the basically multiple regression model that we are using, the concept of partial derivatives, right, or partial correlation. So this whole thing, this whole thing that enabled us to tell a story is gonna hold only if some assumptions are valid. If assumptions are not valid, then your beta hat is going to be biased. Your beta hat is off. Your beta hat, and then the numbers that you're calculating has a large standard deviation or variance, right? So let's see what are those assumptions. All right, one very last thing before we delve into the details of the assumption is the concept of correlation versus causation that I bet many of you guys are already familiar with, but it is worth re-emphasize it one more time. Remember, correlation refers to the linear, so this is super important, refers to the linear relationship between two random variables and how they change together. So for example, obviously all of you guys know that if this is a x1, x2 or x1, y, I don't know, let's say x1, y, what is the correlation? Positive. If I have something like this, what is correlation? Negative. If I have something like this, what is the correlation? 0, right? But as you can see, these are all linear relationship. But what if we have something like this? I urge you to go ahead and you can use Python and simulate these numbers. So for example, the true value in the data is y is equal to x squared, right? And then you can add some noise and then go ahead and calculate the correlation between x and y. So what is the correlation between x and y here? If you use a calculator or Excel or Python, you're going to see that the correlation is 0. So correlation here is going to be actually 0. But does it mean that there's no nonlinear relationship in the data? Obviously there is. You know that y is equal to x squared, and of course we can add some noise to that, right? Y is equal to x squared. It means that there is a perfect nonlinear relationship between x and y, but the correlation does not capture that. So this is very important, guys. I want you to pay attention that whenever we're talking about correlation, it can capture nothing but the linear relationship. So there can be very good, very many times actually, that the correlation is 0. It's not capturing the pattern in the data because the pattern simply was nonlinear. Okay. All right, so that's one thing. The other thing is that causation refers to cause and effect, whether one event is the result of another event, right? So causation is different from correlation. For correlation, the direction can go from x to y or y to x. It's y-directional. But causation, the direction matters. Is x causing y or y causing x? Or basically there's some third variable z is causing both of them, right? So that's the causal effect thing. And remember, regression analysis is nothing but investigating a bunch of correlation, and it cannot prove causality. Okay, so at the very best, we can say, hey, this is our regression analysis, and we come up with some probabilities. With this, let's say with 95% probability, this number that you're estimating, let's say 0.5 for education, is basically valid, right? Something like that. So at the very best, it can tell you numbers with some probabilities. It can never prove causality, right? But the whole point is to go from correlation to causation by checking the validity of a bunch of assumptions, right? So given some assumptions, we hope to get causality with a statistical significance. So this is what we can do. We cannot prove causality, but we can use some, basically the statistical significance, say with 95% probability that's there, right? Okay, so what are these assumptions? Finally, we're ready to look into those assumptions. Okay, we're going to call them the Gauss-Markov assumptions. There are 5 of them, and then later on we're going to add assumption number 6. For all of them, we're going to call them classical linear model assumptions, but we are going to relax the very last one, so we will always stick to this Gauss-Markov assumptions. So let's see what are these. All right, finally, assumption number 1. Linearity in parameters. So this is very subtle, pay attention. So I'm going to give you a bunch of examples and you think about it, which one is linear, which one is not. So we're going to call a model linear if it is linear in parameters, and this is one of the assumptions that we're making. So y is equal to, let's say, beta 0 plus beta 1 x1 plus beta 2 x1 squared plus beta 3 x2 and etc. Is it linear or nonlinear? Again, I want you to pay attention to the coefficients. So let me write a bunch of other ones and then let's do it together. Then beta 0 plus beta 1 log of x1. For fun, we can call this one log of y2 plus beta 2. Then x2 to the power of 3 plus. And then finally we can have y is equal to beta 0 plus x1 divided by beta 1 plus, I don't know, x2 plus u. So I want you to pause the video and tell me which one is linear, which one is not linear, right? And remember, you want to see if assumption number 1 is violated or not. So for first one, just focus on the parameters. Close your eyes on the variable itself. I don't care if there's x to the power of 10, x to the power of 2, or whatever. Look at the parameters. Do you see nonlinearity in parameters? No. So this model is not violating assumption number 1, so it's okay. The second one, again, just focus on the parameters. Beta 0, beta 1, beta 2, that's it. Again, this one is not violating assumption. Let's look at the third one, beta 0, there you go, 1 over beta 1. So this is nonlinear in beta 1. So I'm going to say this is a violation of assumption number 1. So if assumption number 1 is violated, then what's the big deal? The big deal is that the OLS we cannot use OLS to estimate the model, right? So we need that linearity in parameters. When you're doing basically the ordinary least square, where you're minimizing the summation of a bunch of squared variables, you want to make sure that when you take derivative, you can single out for the parameters, right? For the coefficients that you're estimating. Okay, so that's assumption number 1. Assumption number 2, random sampling. This is very, very important, right? Mathematically, we can make some statement and talk about it, but just let's think about it as a very high level. What will go wrong if your sampling is not random? So let me give you an example. Imagine this is your y variable, this is your x variable, right? And imagine, again, remember, we're talking about the entire population, right? So imagine for whatever reason, this is a relationship in the entire population. Okay, so this, we have thousands and millions of all these dots. So this is my population. So I know that in the entire population, probably we are looking for something like this. Y is equal to beta 0 plus beta 1, x plus beta 2, x to the power of 2. And this is a positive number. This is a negative. This is what we're looking for. So this is reality, right? And let's say in reality, I'm just making up some numbers. This beta 1 is equal to 2. This beta 2 is equal to, I don't know, minus 0.5. This is reality. So hopefully we want to get as close as possible to this reality. But if my sample is random, let's say I have observations from here, look at the red ones. Hopefully I use these 20 observations and then I get beta hat 1, which is close to 2, and beta hat 2, which is close to minus 0.5, hopefully. And if that's the case, we say that our estimator is unbiased. We're going to talk about it later on, unbiasedness, right? But in a nutshell, it means that, you know, on average, we're hitting at a target. We are hitting at this true number, right? But what if, I want you to pay attention to this, let me use green, to this green dot. So imagine our sampling is not random. So for whatever reason, we are collecting information not randomly, and for whatever reason, we ended up here. So if I want to come up with a regression fitted line, it will be something like this, right? So this is sample regression function using the green observations, and I will probably get something like this. Y is equal to, again, let's say beta 0 is 0, just for the sake of argument. Beta 1 is going to be a lot more steeper here, so I don't know, maybe it's 3x and etc. Okay, and then this is my estimation for beta hat 1. And as you can see, this estimation is not close to number 2, which was in reality. So we are getting further and further away from reality if you're not doing random sampling, right? So, and that's the important thing. So we know that, and sometimes we have to, as an econometrician, you know, we are given the data and then we wish that the data is just randomly selected. But if the data is not randomly sampled, you know that your model might suffer from serious bias. Okay, so that's assumption number 1 and 2. Okay, assumption number 3. No perfect collinearity and variance of the random variable, the explanatory variables should not be equal to 0. Okay, so let's start with this one, which is simpler to grasp at the beginning. So let's say I'm regressing wage on education. And by the way, this tilde, this is a notation that we use for, we say regressing wage on education, right? And imagine that's the case. And for whatever reason, in your data, you are just looking into these observations, wage, education. You're only collecting information of, I don't know, a cohort of bachelor students, and you're all bachelors. And imagine this is only one variable that you're investigating in the data. So wage is equal to beta 0 plus beta 1 education, and that's it. That's the only thing you're looking at. So let's say they are all 16 years of education, 16, 16, 16, 16, 16, and etc. And obviously you're going to have different wages, right? I don't know, imagine these are hourly wages, 20, 10, minimum wage 8-ish, 30, and etc. If I want to plot this, what do I get? So this is my wage, this is my education, and this is my only, so this is, let's say, education 16, and as you can see, we have 20, 10, 8, 5, 30, and etc. You name it, right? So what is the variance of education here? What is the variance of x? And remember, x is your education. It's 0. So it is violating assumption number 3. Let's see what will go wrong if you're violating that assumption. So guys, imagine you have, this is your data. And what are we doing? We're using OLS to come up with a best fitted line, right? And best fitted line is going to go through this, right? So do you agree that this sample regression function is going to minimize your ordinary least square? We can think of it as mean squared errors, minimizing the squared errors. Because look at that, this is a squared, imagine this is a squared error, squared error, squared error, and etc. So this is minimizing it, right? So as you can see, the red line is minimizing, and the red line is telling you that, okay, beta, let me actually try to erase this one. Yeah. So this is very subtle, pay attention. So red line, it's going to say beta 0, beta hat 0 is equal to, let's say, 10. And what is beta hat 1? The slope is 0. Okay. But what about this line? Do you agree that this also, so sample regression function number 2, this also is minimizing the squared errors? Yes. Because again, we're dealing with the same squares. Hopefully you're following and get the idea. But this one is suggesting beta hat 0 is equal to, I don't know, it's going to be a high number, 30, and beta hat 1 is going to be a negative number, let's say minus 2 or minus 1. But what about this one? Sample regression function number 3. Do you also agree that this is also minimizing? So whatever that number, mean squared error is going to be the same, right? So for example, mean squared error here is 100. I'm making up these numbers. 100 mean squared error, and then mean squared error here is 100. But this one is suggesting beta hat 0 is equal to, I don't know, maybe we're hitting 2, and beta hat 1 is equal to plus 2 now. So which one is the case? As you can see, because assumption number 3 is violated, because the variable of interest, the exponential variable itself is not basically varying, it's not changing, then the OLS is having a hard time pinning down the coefficients, pinning down the estimates of the coefficients. What is beta hat 0? Is it 10? Is it 30? Is it 2? What is beta hat 1? Is it 0? Is it plus 2? Is it minus 2? So as you can see, if assumption number 3 is violated, OLS is having a hard time pinning down the coefficient. So that's one thing. Now, what is perfect collinearity? So perfect collinearity, let's say we have, well, perfect collinearity, the definition is that when the correlation is equal to 100%, right? So, and then we have to make sure that there's no perfect collinearity between our x variables. So what does it mean? It means that, so imagine this is your wage. I'm going to use Venn diagram for this one because it's usually helping students understand better. So it's education, age. So we know that multiple regression model is looking at this, holding age constant, then what is the relationship between basically education and wage? But what if, just for the sake of argument, what if the correlation between education and age, let's say this x1 and x2, is 100%? So this is going to be my wage. This is going to be my education. I'm going to use another color for, this is going to be my, hopefully you're following, age. For whatever reason. Obviously, the education and age correlation is not 100%. I'm just trying to give you an example. If that's the case, then where is your beta hat 1? Do you remember what is beta hat 1? Beta hat 1 is the net effect of education on wage, netting out the age thing. But now, if education and age are 100% correlated, there's nothing left there, right? So if I want to do it in a less exaggerated way, so let's see if I can do that. So for example, this is, yeah, something like this. Okay, so this is age, and then this little, let me do yellow, this little red shaded area, yellow shaded area is going to be my beta hat 1, right? So as you can see, and if that's the case, the model is using less and less information, and then it's gonna having a harder time to pinning down the beta hat 1. And again, in extreme case, when there is perfect collinearity, we know that this is wage, this is education, this is also age. We cannot find beta hat 1. Hopefully you get the idea. So that's assumption number 3. All right, now let's do assumption number 4. This is usually the hardest one for students to grasp. So let me actually walk you through it and see if we can get a good understanding of it. It's called zero conditional mean assumption. So we have to understand what is a conditional expectation, and then what do we mean by zero conditional mean assumption. In English, we say that given any value of x, the errors are on average zero. So let's see what is it. So basically, I'm going to open up this for you. Let's go back to our very own example of wage and education. So let's say this is a relationship. Wage is equal to beta 0 plus beta 1 education. And now I'm going to make a strong assumption and say that, okay, there's nothing else. We're not controlling for anything else in the model. And we're going to call everything else, put it in the error term, right? And you know that behind the scene, this error term is noise. And it's a combination of all other variables, right? So I'm not looking into age. I'm not looking into IQ. I'm not looking into, let's say, I don't know, family income, right? Or family wealth, whatever. I'm not controlling for anything, and I'm going to stack all of them into the error term, right? And let's see, what are we doing? So imagine this is our wage versus education. Pay very good attention. As I said, this is usually hardest for students to grasp. And imagine I'm just only looking at floor level of education. So it's not, the variation is not zero for sure. So we're talking about high schoolers, bachelor students, master students, ignore the scales, and then maybe PhDs, right? And then obviously, the majority of the high schoolers, let's say this is the minimum wage, depending on what state you're living, or let's say just for the sake of argument, it's $10 per hour minimum wage, right? Let's say, yeah, there are a bunch of them getting the minimum wage, and of course there are going to be some of them here and there, right? So for the bachelor's, so I think on average, the wage is going to be higher, master higher, and PhDs higher. So this is what we're assuming. Okay. So let's say, again, this average is 10, and this average is 12. I'm just making up numbers. This average is 14, and this average is 16. So regression is nothing but connecting these conditional expectations, right? So, by the way, expected value of wage given education, if education is equal to 12, is what? Is 10. This is what we mean by conditional expectation. Given the education is 12, go ahead and take the average of the wages for high schoolers. Given the education is 22, go and take the average of the PhDs. Let's say, I don't know, it's 30. Okay, so this is a conditional expectation. And basically, we're saying that this is assumption number 4. We're assuming that if this is my regression, then everything else that I put here in the U term, let me use green, is mean independent from all the x's, right? So basically I'm saying that expected value of u given x is equal to 0. Do you want to visualize it? Yeah, we can. So let's say this is, instead of wage, I'm going to use the u hat here. So these are the error terms. I'm going to use u hat because u hat is observable, u is unobservable, but theoretically you can think of them. When you're using a mathematic term, you can just write u given x, right? And what are these things? So if I have 12, 16, 18, 22, there are a bunch of positive, not negative, right? Remember, these are the residuals. Residuals, hopefully you're following how to go from this curve to this curve, right? And then the point is that we're assuming that conditional expectation is 0. Expected value of u, these error terms, given different values of x is 0. If x is equal to 12, x is equal to 16, 18, 22, you name it, right? So this is an assumption. And this is a big assumption. And let me try my best to tell you why most of the time that's not the case, right? So because you see something like this, and then imagine, and the point is that you're not controlling for anything else, right? So if I write a model like this, then this model, this sample regression function, is telling me a story. And that's a story is, what is a story? Beta hat 1 is equal to, I don't know, let's make up some numbers. Let's say its slope is 0.6. For every additional unit of education and additional year, on average, you're going to get 60 cents more, right? Or $0.6 more. Is this story valid? It is going to be valid only if this assumption is not violated. And this is a big assumption. Why? Because you're saying that everything you put it in the U term is not correlated with X, right? So we have this thing we call endogeneity. That's a weaker form of mean conditional expectation. And then basically it says that if the correlation between U and X is not equal to 0, they are endogenous. If it is equal to 0, basically they are exogenous, right? But look at that. This thing, we had age, we had family wealth, we had gender, I don't know. And of course, part of it was noise. But do you buy this argument that the correlation between age and education is 0? No. But so this, if the correlation is not 0, then this setup is suffering from endogeneity. It means that whatever you put in that error term is correlated with X, and it's gonna make the coefficients, beta hat 1 that you estimated, to be biased. So let me try to use Venn diagram and tell you from the other perspective. So imagine this is our wage. What we're doing in the wage education setup says that this is wage, this is education, this is whatever is not explained, right? So this is the explained part, this is an unexplained part. We can think of it as a representation for U hats, right? The errors. Okay. And we are assuming that those U hats, we're assuming the correlation between those education and then U hats are 0. And my point is that this is a big assumption. And the idea is that if that's correlation is equal to 0, then yes, your story is valid. Beta hat 1 is equal to 0.6. But the problem is that in reality, we know that this U hat has age in it, has family income in it, has gender in it, and it is not correlated with education, right? So it means that the correlation between education and U hat is not 0, and then this thing that you're seeing here is contaminated with some error. So imagine this is your age, this is your family income. So this red shaded area that you see, 0.6, is contaminated with this green part. So that means that your coefficient is biased. So if assumption number 4 is violated, this number that at the end of the day that you're estimating is not a number that you can trust. It does not hold the true relationship in the population. So that's why we're making an assumption. We say, okay, if assumption holds, then this is my story. All right, last Gauss-Markov assumption is assumption number 5, homoscedasticity. So homoscedasticity simply means that same conditional variance. So basically, in the previous slide, we talked about conditional expectation. Now we're going to talk about conditional variance. So we say the conditional variance of U given X, let me use blue, is constant. This can be a number, I don't know, 100. Depending on the scale of the target variable, it can be any number, right? Don't think that it's 100 is large or small, or 0.1 is large or small. It can be any number. It's constant. The point is that the conditional variance is constant. Let's first talk about the conditional variance of U given X and try to visualize it, and then see what will happen if this assumption is violated, right? So again, the idea is that let's going back to the so let's look at the variance of Y given X, because if you're interested in, so let me actually write it down. The variance of, we know that Y is equal to beta 0 plus beta 1 x1 plus, let's keep it simple here, right? If I want to do conditional variance, right, if I want to say the variance of Y given X, so this is a constant. The conditional variance of a constant is 0. This is something as a function of X. If I fix the axis, the variance is going to be 0. So the variance of Y given X is basically narrowed down to the variance of U given X. Okay. So hopefully you can understand where we go, how we go from this to this, right? Basically, this is conditional. If X is constant, conditional on some constant values of X, of course, there's not going to be any variation in beta 1 x1. So that's why we get rid of it, right? Okay, so now we know that. So variance of U given X is basically the same as variance of Y given X. Now let's look at a bunch of examples. So imagine this is Y, this is X. And I'm looking at different values of X. Let me use another color. So this is one value of X, one value of x, one value of x. And I want you to look at the dots and think of the distribution for, or the variance. So as you can see, the variance of these dots here is smaller. The variance of dots here is larger. The variance of dots here is even larger, right? So distribution-wise, I can think of it as this. So these are conditional distributions, right? As you can see, the variance is increasing. So the variance of u given x is increasing. Hopefully everybody is seeing that. So conditional variance is increasing. This one, the variance is decreasing, right? So for this one, the variance of u given x is decreasing. So this is heteroscedastic, this is heteroscedastic, this is also, the variance is decreasing and then increasing. This is also heteroscedastic, right? So what is homoscedastic? Homoscedastic is something like this. We say the conditional variance of y given x. And actually I can go ahead and plot the u given x directly. U given x directly. So let's say this is what we have. If that's the case, then you will see that the conditional variance of u given x is constant. It's a number. I don't know, that number can be anything. Let's call it sigma squared. So this is homoscedastic. Homoscedastic. Okay. In our previous example, when we had wage versus education, what do you think? Was it homoscedastic or heteroscedastic? So let's say this is high school, bachelor, master, PhDs, and we say something like this. The variation in the PhD students is a lot more in terms of wage compared to high schoolers, right? So this is a violation. This is violating assumption number 5. So, okay, now we know what is homoscedasticity, what is heteroscedasticity. Then what? What are the implications if this assumption is violated? So in order to explain that one, we need to pay attention that there are two things that we're interested in when it comes to regression. Well, there are three things, but let's talk about the first two one. Remember, at the end of the day, there is this population regression function out there in the wild world, population regression function. And our goal is to get as close as possible using different samples. So this is sample regression function number 1. This is hopefully, I don't know, sample regression function number 2. And depending on how many samples we use, we end up with hundreds of beta hat 1s, hundreds of beta hat 2s, right? And so what we care about all these beta hat 1s, so let me actually use the right. So this is beta hat 1, red 1, beta hat 1, green 1, beta hat 1, black 1, you name it. We are going to have thousands of those beta hat 1s. So beta hat 1 coming from sample 1, beta hat 1 coming from sample 2, beta hat 1, and etc. Okay. So all these estimates, we're interested in two things. First of all, the average of them. And second, the variance of them. Again, we're interested in the distribution as well, but that's for the next topic. So why are we interested in average? Because we want to say that, okay, if some assumptions are there, on average, we're hitting at a target, right? So it means that if I take the average of this red one and green one, hopefully I get closest to the blue one, right? So on average, we're hitting at a target. So I hope that on average, the expected value of all these beta hat 1s is equal to something unobservable in the population world out there, right? So that's something. Another thing is that the variance also matters, right? Because yeah, if sample regression function 1 is the red one and sample regression function 2 is the green one, as you can see, it's not varying that much, and it's a good news, right? Because if this one is a small, it's good news. It means that your beta hat, whatever sample you use, it's close enough. The variation is small, it's close enough to population regression function. But if you have something like this, I don't know, this is population regression function, and then you end up having something like this. Each time your model is estimating something wildly different. So the variance of beta hat 1 is large. Okay, so we do care about the variance, right? So the variance of our estimator. And if assumption number 5 is violated, if your model is suffering from heteroscedasticity, then the formula for this variance is not valid. So there's a formula for the variance. Again, I'm gonna keep it. I'm just gonna write it down here. But if you're not following, that's totally fine. Again, that's an econometric course. And we're doing it in one module, obviously, but there's a formula for that. The formula is something like this: sigma hat squared divided by basically sum of square x t1 minus r squared j. Don't worry about this formula, but the point is that if assumption number 5 is violated, this formula is not valid because these variances are not constant. If the variance is not valid, then you cannot trust on the standard deviation of this number. If you cannot trust on the standard deviation of this number, then you cannot trust the t-stats. So basically that means that you might get fake significancy if the model is suffering from heteroscedasticity. In simple English, if you remember, we have regression tables, there's a bunch of stars at the top of it. So it means that those stars, 1 star, 2 star, 3 stars, are not valid. You cannot trust them if the model is suffering from heteroscedasticity. And guys, remember, don't lose the big picture. At the end of the day, we're trying to tell a story, and we hope that that story is statistically significant. If assumption number 5 is violated, maybe we are doing fake significancy. That's why assumption number 5 is also important. All right, you did it. Here you go. Here's our 5 Gauss-Markov assumptions. Here's a summary. Again, assumption number 1, 2, 3, 4, 5. And then let's see, theoretically, why do we need these assumptions in one simple slide. So we're going to say, if I have assumption number 1 through 4, then it is mathematically proven that OLS estimators are unbiased. This is a big deal. Again, do not lose the big picture. At the end of the day, you're a storyteller. You want to hope that this story that you're telling on average is hitting at a target. So what does it mean? It means that, again, based on the sample that you used, you come up with a number for beta hat 1, and that number was, I don't know, 0.5 for the education thing, right? So if it is wage versus education. And we know that there are hundreds of these numbers out there, depending on what sample we're using from population. And if I have assumptions from 1 through 4, it is guaranteed that on average, we are hitting at the true relationship in the population between education and wage. So this is kind of strange. This guy is unobserved. This is observed. And then can you say that these are equal to each other? So that's why, again, we are econometricians. We make some assumptions and we live in that fancy world, right? And then we can mathematically prove that on average, you're hitting at a target. Our story, if I repeat this sampling thousands of times, you're hitting at the right number. And this is a big deal. Then if we add assumption number 5, we can say something about the variance, right? So now we know that the averages, on average, we're hitting at a target, but what about the variance? Are we hitting at a target? Let's say this is your beta hat. Let's say this is reality. In reality, the beta hat out there was 0.5. The true relationship between education and wage for the entire US labor force is 0.5. Every additional unit of education, holding everything else constant, on average is going to increase your wage by 50 cents, right? And so this is my beta, right? And then are we talking about something like this or something like this? Which is the case? Which one is better? So if this is a distribution for your beta hat, is this one better or this one better? Hopefully you're telling me this, right? Because both of them on average are hitting at a target 0.5, but one of them is hitting at a target with a very large variance, this one. The other one is hitting at a target with a small variance. So this one means that from sample to sample, this beta hat is changing a lot, right? So for example, one time it's 0.1, the other time is 0.9, the other time is 1.5, and etc. And then the variance is large. If the variance is large, it means that this number that you're reporting, whatever it is not statistically significant. We're going to do some hypothesis testing by knowing the distribution of beta hats, right? So that's why the variance also comes into place. And the way that I can trust these numbers for the variance of beta hat J is that if assumption number 5, basically all the assumptions, look at this blue shaded thing, 1 through 5, is not violated. So if the assumption 1 through 5 is not violated, I can trust this number. And then based on that, I can say if this story that I'm telling is statistically significant or not. So now we know the average, we know the variance. The last thing for us to do some hypothesis testing is that what is the shape of this distribution? What is the shape? Is it normal? Is it standard t? Is it chi-square? What is it? Okay. And obviously we need to make another assumption to tell something about the shape of the distribution. And why do we need the shape of that distribution? Because we want to do some cool hypothesis testing. Okay. All right, let's put it all together. So basically the idea is that if any of these Gauss-Markov assumptions 1 through 5 is violated, it is important to exercise caution when interpreting the results of econometric models, right? Because here the model's predictions and parameters estimates might be completely unreliable, right? At the end of the day, we are doing econometrics and not machine learning, not deep learning, for the sake of its simplicity and interpretability. But that story is going to be valid, that interpretability is legit only if the assumptions are there. So please, guys, you are taking the machine learning course, and then you should know that, okay, if this is econometric, no, if I use the econometric approach for linear regression model, if I want to tell a story, I should not simply close my eyes and look at the number of stars on the top of the, I don't know, the coefficient, say that, okay, this is significant with 99%. This is, I don't know, with, let's say alpha is 5%. 5%, at 5% it is statistically significant. That's not the end of the story. You have to check the validity of all the assumptions, then you tell your story, okay? So obviously there are some statistical tools and tests to verify every single of these assumptions, but that's beyond the scope of this course. All right, I think you know what you need to know about basically what is the econometric approach when it comes to linear regression analysis, what are the assumptions, why do we need them, and why without any of those assumptions the story that we are telling is not valid, right? So the rest of the slides is basically some technicalities. I'm going to walk you through some quick review of the hypothesis testing and things like that. So if you know all these things, just feel free to skip the rest of it, and I'm going to see you in the next module, which is module number 4. We're going to go over the fundamentals of machine learning. But if you're enjoying it, just stay around for the next 10 to 15 minutes. Okay, so what do we mean by statistical inference in regression analysis, right? And this is something that we will not talk about, I think, mainly at all when it comes to the machine learning approach, right? So far, we know that the 5 Gauss-Markov assumptions, based on them, we know something about the expected value of the beta hats and the variance of the beta hats. But what about the distribution? Why do we need the distribution? So far, we don't know anything. So it means that we need to make one more assumptions, right? Yeah, that's our assumption number 6, and that's a super strong one. So the bad news is that it's very strong. It's most probably not holding in the real world. But the good news is that we can relax that assumption. So what is that assumption? The assumption is telling you that the error terms, those U's, are normally distributed with average 0 and variance, a constant variance of sigma squared. If we have this assumption, we're going to come up with something called classical linear model assumptions. And under classical linear model assumptions, we know that the distribution for our beta hats is going to be normally distributed. Okay. Again, we're going to relax this assumption, and then we're going to end up with a t distribution, student t distribution for beta hats. But even if it is t or normal distribution, the good news is that now we can do some hypothesis testing. You know, we can look at the left two-tail hypothesis test, one-tail hypothesis test, and etc. Okay. And again, the good news is that if the sample size is large enough, remember, the whole point was looking, trying to infer something about the population by looking at a sample. If that sample is large enough, thousands of records, hundreds of thousands of records, then we can relax this assumption number 6. We don't need it because of the central limit theorem, right? And the central limit theorem simply says that, your sample estimates, if the random variable, if the sample size is sufficiently large, then this sample estimates, in this case beta hats, are going to be approximately normally distributed regardless of the shape of the parent distribution. It can come from any kind of distribution, but the sample estimate themselves are going to be approximately normally distributed. All right, now with the classical linear model assumption, CLM, we can say if this story that you're telling is statistically significant or not, right? So let me give you some background. So imagine this is wage is equal to beta hat 0 plus beta hat 1 education plus some u hat. Let's write the estimated version of the model. Let's say wage. I'm going to put a hat because this is the estimated version of the model. And let's say we're talking about 5 plus 0.6 education. So this is the estimated version of the model. And the whole point is that, is this number legit? Is it statistically significant or not? So in the population, so we're inferring this number from the sample, right? I want to say, can I say something about the population? If education increased by 1 unit, the wage is going to increase by 60 cents. In order to do that, we have to come up with a statistics. So for those of you who are familiar with this guy, this is our t-stat. So let's say t-stat is equal to this. What are we doing? We're saying that whatever you estimated, let's see how far it is from whatever you want to test hypothetically, and then divide it by how wide. This is simple normalization, right? How wide is the standard deviation or standard error of those estimates, right? So for example, and again, guys, remember this guy is unobservable. That's why most of the time we're going to test it against, is this beta j relevant or not, right? So my hypothesis is that, the null hypothesis is that, let's say beta education is equal to 0. An alternative is beta education is not equal to 0. If I do not equal to 0, we're doing two-tailed tests. If I do, for example, greater than 0, we're doing one-tailed test, and etc., right? So the cool thing is that, and pay very good attention, hopefully you have to understand why these are betas, not beta hats, right? So pause the video and answer that. Okay, so these are betas because you're interested in answering something about the population. This is unknown, and you're assuming that if it is 0, and then C, you want to see if it is relevant or not, right? If I put a beta hat, it doesn't make any sense because beta hat is observable. Beta hat education in this example is 0.6. It doesn't make any sense to test if it is 0 or not. So what we're doing here is that we say we are going to construct that t-stat. Say, okay, the t-stat is, in reality, well, in the sample, it was 0.6. You want to test if this education at all is relevant in the population or not. So let's say if it is equal to 0 or not. And then divided by a standard error. Let's say a standard error is 0.2. If I get a number like this, it's a large number. It's a good number. It means that, that assumption that you had, which was basically the coefficient of education is 0 in the population, it's not valid, right? Because this large t-stat, if I want to do it two-tailed test, so let's say, I don't know, t-stat t here is equal to 3, and then we are doing 5% or 10% significance level, 5 on the left, 5 on the right. Obviously, we're going to reject the null, right? We're going to reject the null that this education doesn't matter in the population. And this is a powerful tool that Econometrics is going to give us. And guys, just pay one last time attention that this whole thing that we did here, if any of those assumptions is violated, for example, you cannot trust this number because, let's say, assumption number 5, the model is suffering from heteroscedasticity of the data, and then I cannot trust this number. If I don't trust this number, I cannot trust this number. If I don't trust t-stat, I cannot say if this hypothesis is legit or not. So hopefully you get the idea that why we did all these assumptions to enable us to just validate the basically hypothesis that we have. Say something is statistically significant. Alrighty, the very last slide, I'm going to talk about the evaluation metrics when it comes to basically linear regression models. So these are the performance metrics. So the most famous and classical one is R squared. This is the goodness of fit, also we call it goodness of fit, and basically it tells you that from the entire variation of your target variable or explained variable, what part of it is explained by the data, right? So there are different formulas for that. I'm not going to dig into the details, but hopefully you, from your econometric course, you remember these kind of concepts. R-squared itself is just suffering from the fact that if you keep adding or if you keep making the model more complex or adding more variables, the R-square is going to increase no matter what. Well, actually, I can use a Venn diagram and tell you what do I mean by that. And so, for example, this is your wage, this is your education, right? We can think of this as an explained part of the variations in the wage. And again, the representation of the R-square, right? The Venn diagram analogy is interesting, but we should be careful about, these are not exact numbers. To ignore the magnitude, just these are some representations. If I add age, this is going to increase. If I add gender, this is going to increase. If I add, so it seems that no matter what, if I keep adding k, the R-square is going to increase. But that's not necessarily true. So we have to penalize this R-square such that if we increase the complexity of the model, if we keep adding more variables, then it's going to penalize the R-square. And this is exactly what we're going to do with the adjusted R-square. So there's going to be a trade-off between the two. At some point, you will stop increasing the number of variables because it's hurting the model instead of helping it. And this is what's going to be captured by adjusted R-square. There are some other popular metrics that we use. Another one is mean absolute error. Again, these are your residuals. This is absolute residuals, and we're taking the summation and divided by the n. So this is mean absolute error. We can also report mean squared error. So again, in order to avoid the pluses, minuses canceling out each other, we're going to square them and take the average. So this is our mean squared error. And by the way, this is what we use in the OLS for minimization optimization problem. We minimize this mean squared error to find the best fitted line. Okay, then we can have MAPE, or mean absolute percentage error. Well, let me use red. This y minus y hat is your error. Y minus y hat divided by is your percentage error. This is absolute percentage error, and we are summing, dividing them by n. So multiplying by 100, report the number in terms of 100. So this is mean absolute percentage error. This is something also sometimes we use. And lastly, which is this one, which is the square root version of the mean squared error. So the reason that sometimes we go from these things on the left to these things on the right is the more interpretability. For example, the units of mean squared error, I don't know, if your y variable is dollars, the unit of mean squared error is going to be dollars squared. It doesn't make any sense. So that's why we're going to take a square root. So the unit of this one is going to be dollar. So the unit of RMSE is the same as the unit of your y variable. If it is dollar, it's dollar. If it is percentage, for example, interest rate, it's going to be percentage. And yeah, and then this mean absolute error, it's a number. It doesn't make any sense by itself, but if you report it as a percentage, it makes a lot more sense. So yeah, there you go. That's all the evaluation metrics. Well, relatively all the evaluation metrics we use for linear regression. And that's sum it up, our module number 3, linear regression models, econometric approach. Until the next one, take care.